Okay, so this is Drinking the Free Kool-Aid. Before we begin, I want to make some acknowledgments. So a lot of the content of this talk builds upon ideas proposed in the book Functional Programming in Scala, which is by Brunar Jarnason, if I'm saying his name correctly, and Paul Chiasano. An excellent read. Highly recommend you read it. And I also consider this talk to be a prequel of sorts to another book, or sorry, not a book, but a presentation that Brunar Jarnason gave at Scala Days in 2014, titled Compositional Application Architecture with Reasonably Priced Monads. Okay. So I don't think I'm actually the first person to say monad at the conference. It was mentioned in a slide, so I thought I was going to be the first. I guess not. So when people hear of monads, for some reason, this seems to inspire fear in people, and it's really not that bad. As soon as you learn some of these concepts, if you're like me, you start to see that they're applicable all over the place. But I will say that the concept, at least when it comes to the free monad, for me took a while for me to understand, and so if you end up confused at the end of this talk, well, I guess I didn't do my job. But I'll also say that you're not alone. There are plenty of other people who have also had a hard time understanding these concepts. And for me, I had to come back around, not once, not twice, but a few times before I really understood these concepts. And I think actually looking at code and writing the code is what gave me the intuition. So this is an introduction to the idea of the free monad, and I also want to say, originally, if you read the description for this talk, I had anticipated doing a lot more live coding, but at the behest and advice of a friend, in order to garner better intuition of these concepts, he recommended that I do less of the live coding and more of the slides. So I apologize if you're here for more of the live coding. Okay. So why do we care at all about this concept of the free monad, right? Why do we care? So let's take a look at a program here. Okay, very simple kind of imperative style program. We're leveraging Scala's syntactic sugar, where what we have is, it looks like an imperative program where we're asking for a Twitter handle, and we use that information to go out and fetch tweets for that Twitter user, and then we want to display them. Okay, so if we have a program that looks like that, let's look at maybe some of the things that we can do with that program. Actually, before we do that, okay. So I'm going to take that program and I'm going to run it in the terminal. And here I'm just displaying a prompt, and I have a default value. This is Rob Norris's Twitter handle. And we're going to go out and we're going to fetch his tweets, the last two tweets. All right, so that same program is going to work unchanged in the browser. Okay, so we're going to fetch some tweets. So William here saw my talk on free monads before I gave it. It's very prescient. And then here's Rob Norris's tweets. So we have the same program, but executed in two very different ways. All right, so how do we achieve that? Let me see if I can work my way back to my slides. Okay. So we made no changes to our original program, yet we were able to have two different versions of it. How do we do that? Okay, so enter the free monad, right? The free monad is just another tool for us to use as software engineers. We have lots of them. And one of the goals, one of the takeaways from this presentation is to help us to learn to use the free monad judiciously in a safe way. So you might be asking yourself, again, well, why do I care? Well, the free monad is going to give us purity of abstraction, reusable definitions, and it actually allows us to defer effects. So as functional programmers, we often like to we like to bottle the effects, or we like to push effects and side effects out to the edges of our programs. And the reason why we do that is to enable reasoning about how we've developed and composed our programs. So let's talk about microservices, or services. There's our old friend, Steve Ballmer. Okay, so Twitter and other companies like Netflix, they might have tens or hundreds of microservices. And how do you coordinate, how do you orchestrate across all these microservices? So say I'm Netflix, and you've logged in, I want to display your username, and I want to fetch some movies for you. I might have to fan out to all these different microservices. I might end up contacting the same microservice multiple times. I might ask for the same piece of information multiple times if I'm not careful. So what would this look like in the imperative landscape? You would end up confusing a lot of your logic, or mixing it in between caching and batching. So what if I told you that you could achieve these, you could achieve the caching and the batching, and you could eschew the caching and the batching, and instead just think about what it is you want to do and not how you want to achieve it. All right. So that's where, it's another plug for, obviously, the free monad. Okay. So for the rest of this talk, this is what we're going to do. We're going to review some fundamentals. We're going to look at some code. We are going to get some intuition about the way this works, and also intuition about the free monad. We're going to look at some more code, and then quick wrap up. Okay, so a quick aside about design patterns and mathematical rigor. So design patterns are very useful abstractions, right, that come up, after we see repeated uses in our programs, and so we end up coming up with these patterns. But what I really want to say is about the abstractions that we're about to just review really quick. These are abstractions that have also come up. Many people have seen it, and they cross many different disciplines. So not only do you see its application in computer science, but you also see its application in disparate areas such as music theory. So first up is natural transformation. Again, I'm not the first person at this conference to say natural transformation. I was quite surprised by that. So we are going to concentrate not on the theory, but more on the pragmatic ideas behind these concepts. So a natural transformation says if I have two type constructors, an F and a G, so if it helps, think of an F as like an option. So the type constructor in this case, if you notice, there is one underscore there for the type constructor, which means it has one type parameter. So if I have an F and a G, and I have an apply method, and if you notice, apply is polymorphic, so it takes a type parameter A. So given an F of A, I can convert into a G of A, all right? So, and down below, we just have our little arrow there, which is just an alias for natural transformation. And the reason why we want to use the little arrow is because Scala gives us some nice sugar to reorder those type parameters. So we can put the F arrow and then the G, okay? So a simple example, so we can get some intuition. We have our option and our list classes. We see that option has a single type parameter and list as a single type parameter. So if we use option and list as type constructors, we have our option to list, which given an option is very easily converted into a list. In Scala, we just call toList on the option, and in that case, we have an option, or we have a list, sorry. Okay, so next up, monoids. Okay, so let's concentrate on the append there. So a monoid says if I have two A's and I have this append method, I can take those two A's and I can then I can produce a single A out of those. Okay. So a canonical example is maybe string concatenation. So how do you append two strings together? Well, you simply concatenate them together, right? And so a zero says if I use a 0 with the append, so if my A1 is a 0, my A2 there is some other string, and if I concatenate my 0 to my A2, then I just get my A2 back, right? Okay, so a lot of these abstractions, I'll also say, have laws associated with them. So we are going to, in large part, ignore the laws in order to concentrate more on the important concepts later on in the talk. Okay, so we have more free things than a free monad. We also have free monoids. So a free monoid basically just says, I don't know how to append. So what I'm going to do is I'm just going to stuff one A next to another. And if we do that, we get something that kind of looks like a list of sorts. Okay, so moving along onto a functor. So we have a type class kind of version of the functor where we are taking a type constructor f, so functor is higher kinded. And we have a map to type parameters a, b. So given an f, okay, so you can consider f to be our payload. So it can be an option or it could be a list. So given an option, okay, and a function that goes from a to b, how do we produce a new option of type b now? Okay, so there is something called the free functor. So we have free monoids, now we have free functors. So a free functor is also known as the Kool-Aid. And what that says is I have a functor, but I don't really know how to map. So I have my f of a. I start off with the identity function, a to a, and then as you try to map over me, I'm just going to store all the things, all the functions that you're giving me. Then at some later point, maybe I'll be able to actually to run that and get an f, in this case, an f of c out of it. So it seems somewhat useless. Why would we do this? Okay, well, it kind of seems like that on the surface. Except for what we'll see later on is that the free functor and the Kool-Aid actually enables us to get a functor for any type or any type constructor f. We get it for free. So even if that f is not actually a functor itself. Okay. All right, so monad. So monad says we have a type constructor m, pure. We have a pure operation which says given something of type A, then I want to create an M of A, which means, so let's use option as an example. So if I want to lift a value, like a string, any arbitrary string, and I want to turn it into an option of string, well, the monad, the monad for option would describe how we can do that. And flat map here, it would take an M of A and a function that goes from A now to M of B. Okay, so this is, what flat map says is, if you have an option of string or anything, any M there, I know how to, again, if you look at the function there, you'll see that it takes an A. So it says that I know how to pull out the value that's wrapped in my option and give it to you, and then you produce a new M of B, so that, or a new option. Right? So you could choose to return some, you could choose to return none. So in this way, monads are encode sequential computation, if you think about it. Now, monads are also nominally functors just because we can derive a map very easily in terms of pure and flat map. So another quick little slide on sequencing computation. So quick example here. We're composing two futures together, and where we have the value 1, error future 1, that's just extracting a value basically out of the future, and then at that point on the next line, we have value 2, and then at the very end we're yielding value 1 and value 2, so we're just adding those two values together. Okay, sorry. I got ahead of myself a little bit in my mind. So okay, so as a result of this, if you look at value 1, and if we were to desugar this, you would see that the desugared representation of this actually just results in a series of flat maps and maps. So you can think of value 2 as being kind of the rest of the program that is yielded as a result of evaluating the first line. If that doesn't make much sense, my apologies. Come find me afterwards. Okay, so I also want to touch briefly on the identity monad. So here what we have is it's almost a type-level version of a monad, where if you look, we have type ID of A, and that equals A. Okay. So at runtime, the fact that we're using this, that we're using ID is almost shed completely. Okay, it's almost erased. And what the identity monad basically says is, even though you give me something to sequence, I'm just going to strictly evaluate it right then. Okay, so it's almost a pass-through. It almost does nothing. Okay. Okay. So moving on now to the free monad. Okay, so repeat after me. A free monad is basically an AST, or an abstract syntax tree, plus an interpreter combined. So an abstract syntax tree basically just expresses computation as data. So it's more the what of what needs to be done. And we have an interpreter which gives meaning to our data. So that's how how it will actually be executed. So I have a math problem I'm going to propose, and it should be pretty simple for all of us here. So what's 1 plus 2? Okay, again, pretty straightforward. But let's think about how do we express what 1 plus 2 is in terms of an abstract syntax tree. Okay, so let's cut over to the code. Okay, so simple application here. And we are going to define an abstract syntax tree that represents mathematical expressions. Okay, so we're going to start off with a sealed trait, expr, short for expression, and we're going to create a case class, short for a constant value. In this case, it's just going to be an integer. It's going to extend expr. We're going to create another one called add, which takes 2 operands, each of type expression. It itself is an expression. And we'll create one called subtract. Okay. All right. So, okay. So what we've been able to achieve here on line 13 is basically a representation of what it means to add 2 values, or sorry, it's more an AST that represents the mathematical expression of adding 2 values. So given this is fine and good, but now what can we do with it? Okay, just a second. Okay. All right, so we have our AST, but now we need to give meaning to it. So on line 17, what we have here is an evaluate method. And that takes our expression, and using recursion and also Scala's pattern matching and extraction, we can produce an integer value out of the expression that we gave it. And this will work for any arbitrary AST that corresponds to a mathematical expression that we give it. So if we were to actually run that, we would see that 1 plus 2 is actually 3, right? A lot of work for just that. But here's where the power starts to come in. So given an AST, we can have a different way of expressing that, or evaluating that same AST. So here on line 25, I have a toString, which in this case is taking that AST, and instead of actually producing a value out of it, instead of actually evaluating that mathematical expression in terms of producing another int, we are actually going to evaluate it and produce a string which represents that expression. So let's go ahead and run this so we can see what we get as a result. Okay. So on the first line, okay, this line right here, okay, that's the result of executing line 23 in the code above. Okay, so we've actually taken 1 plus 2 and executed it. These lines below are, well, simply, so this is calling the toString basically interpretation of our AST, and we get 3 plus 4 plus 5, similar to how we had defined it in terms of our AST. We have slightly more complex expression down below on line 32. And we have a series of assertions on 33 through 35 just to do a quick sanity check. All right. And I do assure you those assertions are actually executing. Right? They are actually checking that that's true. Okay. Okay. So we have been able to give meaning to our AST. So what does this have to do really with the free monad? Okay, well, we're getting there. Okay, patience, everyone. Let's take a look at the way that we define the free monad. So we have a seal trait here, free, and it takes a type constructor f, where f is a payload of sorts. In our previous example, f would be our expression, but we would need to modify our expression to have a type parameter, which is what the underscore there is referring to. And then we also have this type A, which is the type that will result that will be the result of evaluating an instance of our free monad. So what the free monad gives us is actually an AST that describes monads. Okay? So what we do is we think about what are the operations that a monad does, and how would we reify those operations in terms of data constructors? Okay, well, so we have something, well, with monad, we have the pure operation where we take something of some arbitrary type A, and we want to lift that into the context of the monad. So how do we lift that into the context of the free monad? Well, we define a data constructor called return, and it's a simple case class, and we give it a value. Okay, and so now how do we do the flat map operation? Well, very, very similarly. Okay, we take an instance of free that you already give me and a function that goes from A to another to a free of the same payload type, but a potentially different kind of return type. And so once we have those data constructors, we can go back to our definition of free. We can define map and flat map. So map is fairly simple. We define that in terms of flat map, and we use the return data constructor. And we have flat map down below, which all we do is we stuff the current instance into the flat map data constructor, and then we also provide a method that basically carries forward your function. Okay, so a simple example of how this might be used, and it may not be entirely clear at this point why we want to go through all this trouble, but so the free monad is actually itself a monad, so you can use it in a for comprehension just like you would with any other monad that you're familiar with. So here we have an instance of return, and return extends free, and we're just composing together a bunch of returns together and yielding hope it works. If you recall, this is just syntactic sugar, where each item in the for comprehension gets desugared into a series of flat maps and maps. So this is actually what's going on under the hood. So once we do all this, what we're really getting is something that looks like this, where we have a series of actually nested data constructors. Okay. So what is it that a free monad is actually doing? Well, a free monad is like a functor, except it doesn't know how to do a join. So joins here take an f of A and shed one layer off of that and turn it into just an f of A. So what you end up getting is you end up accumulating all these f's, right? And then the question becomes, if we've accumulated all these f's, how do we get rid of them? Okay. So what I am saying is we do have a monad for monads, and it doesn't seem on the surface that they're really doing kind of monady things, right? So a monad should be doing a join. So how are we going to compensate for that? Okay. So how do we do that? So how do we remove those layers? So we define another method. We'll call it, in this case, run free. Takes two type constructors, F, G, and an A. So what that says is, if you give me an instance of free, okay, an instance of this free monad, and you give me a natural transformation, which takes me from my F to a G, plus, if we add the constraint that G has to be a monad itself, then I can shed those layers and actually evaluate the free monad that you gave me. Okay. And so what we end up getting is a G of A. Okay. And so why this might be important. So if F is, so let me back up. Let's say, why is this version actually somewhat important? If we express run in these terms, where we have the natural transformation, and we make the imposition that G has to be a monad, then that allows us to get around the fact that if we didn't have these constraints, F would have to be a functor. And so anyway, so this just allows for more, let's see, what's the word I want to use? It's more open, it's easier to use. Okay. So what do we mean by free? Okay, how is this actually free? You know, free as a bird. Well, so if F is actually a functor, in this case, we actually get a monad without having to do anything extra. We automatically get a monad for it. So it's defined in functional programming in Scala as a free in this context means generated freely in the sense that if you have a foo, where a foo might be a monoid or a functor or a monad, so you have a free monoid or a free functor or free monad, then that free foo itself doesn't need to have any foo structure of its own. Right? So free monad doesn't need to actually have all the monadic structure that's required with scaffolding that's required. Okay, so if you recall, at the beginning of the talk, we showed a brief example of taking a single program Let me bring it up. Okay. So this program from line 13 to 20. So we took that program and we ran it in the command line. And we also ran it in the browser. So how do we achieve that? Okay. So this is where it starts to get interesting. So let's go to the definition of this tell here. Okay. All right. So what we've done on line 10 is we've defined this thing I'm just calling nominally an instruction. It has a type parameter A. And then we define an AST that describes, in this case, interacting with the user. So we have an AST that describes prompting a user with some bit of information, and we have an AST that also describes getting information from the user. So if we have something that is an abstraction over these concepts, it's just an AST, then actually applying it is more the job of the interpreter. We also have on lines 15 and 16, we have data constructors that represent fetching tweets for a user and then also displaying them. On lines 18 through 22, what we do is we have a series of, in air quotes, smart constructors that take our values and lift them into an instance of free. The reason why we do this is so it's more out of convenience, so we don't have to litter our code with returns, with the return data constructor or the flat map data constructor. Or in this case, there's a suspend data constructor, which is more a convenience thing, which we won't really have time to get into at this point. But so once I have these smart constructors, I'm able to compose them because these smart constructors are returning instances of free. Free is a monad. Okay, so we can compose them just like we can any other monad. And if you recall, once we compose it, we actually get a series of nested data constructors. So this is well and good, but now how do we get rid of those layers? Okay. So we'll come over here. This is the terminal or the console representation of our program. So what we do is we have this thing called standard evaluator, And it is a natural transformation from our instruction, where an instruction, if you recall, is actually a data constructor for tell or ask or get tweets or display tweets. So we have a natural transformation from the instruction over to ID. So ID is actually the identity monad. So if we have all the scaffolding in place, then given an instruction, how does that actually result in printing to standard out or reading from standard in, right? So that's what this standard evaluator is doing here. Maybe it should be better, it would be more properly named, standard interpreter, standard out interpreter. But this gives the mapping from our AST into some concrete operation, which might be site affecting. Okay. So given that interpreter, we can run it. We look on line 50 there. So we're giving the program, we give it an interpreter, and we're able to execute it. And from there, right, it'll print out to standard out. Let's just run it again, huh? Okay. All right, so what's interesting about this is the program unchanged works like this, just as before. Thanks, Rob. I assume that's in reference to this talk. Okay. And so, but we can also apply a different interpreter. So we have this thing called the test evaluator. We're here, what we're going to do is we're going to give a series of pre-canned answers. So think about using this in terms of a unit test. Okay, so we define our single program, which we can test and then interpret in different ways depending on the context in which we want to have it run. So with test evaluator, we give a series of pre-canned answers, and then when it comes to actually printing something out, we just return units. We just ignore it. When something says, "Hey, you need to respond to an ask," so when our run method is shedding the layers and it comes across an ask, it's going to call this natural transformation and it's going to say, "Okay, here's the ask. What do you want to do in response to that?" In this case, we're just going to basically pop an answer off of our list, our sequence, and then we're going to return it. And then on line 31, we're actually ignoring whatever usernames that you're giving me, and I'm just going to give you back a series of tweets pre-canned tweets that I want you to use. And so if we run this program now, you'll see that it's not going to prompt us for a username. It's going to directly execute with the interpreter that we provided. Okay. So now the question becomes, okay, so this is cool with the standard out version. How about the web browser version? How did that work? Okay, so let's come over here really quick. Okay, so the web browser version actually looks very similar. Now, I cheated a little bit in that I'm hiding some of the actual rendering of this. If we go over here, you'll see that we're using some of the Scholar.js libraries in order to construct some HTML. But nominally, the program itself is unchanged. So let's come over here. So I actually do, in this case, two passes over our program. On the first pass, I go over it with something that knows how to render the AST. So it's producing your divs, your labels, and your text boxes. And then, so that's just for displaying purposes. And then when you click the button, I do another pass over the same program. And I use another interpreter which knows how to pull the values out of the text box and then execute on it. And when we do that, right, we get this again. Okay. Okay, so repeat after me. Okay, a free monad is simply an AST and an interpreter. And then, so you might ask, can I compose different Fs? It's a great question. You read my mind. How did you do that? So what I mean by this is, so say we have a foo of A and a bar of A, and we have two instances of free. So one is it's a free of foo, and the other one is a free of bar. Can we compose these things together? Actually, we can. So there's something called the coproduct, and it's not something that we really have time to treat in this presentation, but you can use these things, these coproducts, in order to compose basically different Fs together. And if you're interested in that subject, I invite you to read the book, Data Types a la carte, and I don't think I'll pronounce his name correctly, so moving along. You can also watch the movie. So this is Runar's talk that he gave at Scala Days as well, where he treats this topic probably in much greater depth than I'll be able to here. Okay, so some things that we didn't have the time to really get to is trampolining. And so again, if you read the book or watch the movie, you'll get some more insight and intuition into what trampolining is and how you can have different versions of run that account for trampolining. Okay, so honorable mentions. So there are libraries already out there, CATS and Scala Z, or Scala Z. I'm not going to get into that war. I say Scala Z, so that's that. So CATS and Scala Z both have their versions of the free monad that are in there. They are pretty similar. So you don't need to code all this up from scratch. You can just leverage what everyone else has already done for you. So other resources, Learning Scala Z, Data Types a la carte, Free Monads, and the Yoneda Lemma, and a talk by Noel Welsh, or actually it's an article, Free Monads Are Simple. Where can you get the source for this talk? There it is. The slides will be available at some point, and so you can get the link there from the slides later. And that's it. Thank you. Okay, so questions. They have to be gentle. I wouldn't put myself at Rob Norris's or at, who am I thinking of? Dibblego, Tony Morris. Right? I wouldn't put myself at their levels, so be gentle. Questions? Can you repeat the name of that video? Compositional application architectures with reasonably priced monads. It's a mouthful. Yes?
Can you go back to the slide where you actually define the natural transformation?
Yes, I can do that. All right, so I don't want to get too deep into the category theory concepts of this. We'll just say pragmatically right now, as it's defined right now on this slide, right, there are really no constraints, right? So F is any type constructor. Yeah, we can talk afterwards if you want some more insight. Yes?
So basically you said that free monad is a functor that doesn't know how to join.
Mm-hmm.
But you also presented a free functor that is a type constructor that doesn't know that it's a functor. And so it's a little unclear. So would it be useful to have a free monad that's a type constructor that doesn't know it's a functor and doesn't know how to join both?
So, okay, so the question is, would it be useful to have a completely free monad that's completely free? Yeah, sure. Actually, if you think about using the free monad in conjunction with the free functor, it does become actually very useful, because then your type constructor F doesn't itself need to also be a functor. Yes, so yeah, there is useful utility there. Oh, great. Okay, so that was a plug for Scala Z, right? Over cats? Yeah, okay. Any other questions? Okay, then thank you very much.